This is John Whitaker for the Probability Graduate Level class, and today we're going to have an extended video which will make up our 25th and 26th video lectures. And today the topic is that of a random graph. So we're going to get started by talking, first of all, just what is a graph, and then move on to a random graph, and then we're going to be interested in the probability that a random graph is connected. That will involve a theorem and a main lemma. That's what we're going to do during this video lecture. Okay, so as a definition, a graph consists of a set V called nodes, set V of elements, called nodes, and a set A of pairs of elements from V, or of V, I'll say of. Called arcs. So that's the definition of a graph. But we generally can write down pictures of a graph. So let's talk about pictorially what we mean by graph. So pictorially, we represent a graph by drawing circles to represent the nodes, and then we're going to use lines to represent arcs. Let me describe that a little better. And drawing lines between nodes I and J when I comma J, that pairing, is an element of A, or is an arc. Okay, we're going to look at some examples of that. So here, if I have V is equal to the set of nodes 1, 2, 3, 4, 5, and A is equal to the set of pairs, so let's say 1 to 3, 2, 3, 1, 5, 2, 4, and 2, 4, and again 1, 1. Okay. Then here's where we can draw this. So here's 1, 2, 3, 4, 5. Okay. So we're saying that 1 and 3 have an arc between them, so that line connecting. 2 and 3 have an arc between them, so that's that arc. 1 and 5 have an arc between them, so there's that line. 2 and 4 have an arc between them, so that's that line. 2 and 4 have another arc between them, so I'll draw another arc. Okay. So there are 2 arcs here. And then finally, we have 1 and 1, and so I'll draw that arc. So that's a representation of this graph. One way for it. And the next thing I want to talk about is this one-to-one arc. Okay, so that's a definition. So here, I, comma, I is called a self-arc or self-loop. So that's the definition. Okay. The next thing we want to talk about is working our way towards what I described that this lecture will cover, and that is connectedness for a random graph. So first of all, working our way towards connectedness. We're going to give a definition for what it means to be a path. So in a graph, there exists a path between node I and j, to node j. And here we have I and j being different nodes. So if there exists a sequence of nodes I'll say I sub 1, I sub 2, I sub 3, all the way up to I sub k, and then finally j. Such that there's arcs, a list of arcs that connects each one of these pairs, or involving each one of these pairs. Here's what I mean by that. So that's that I to I1, I1 to I2, I2 to I3, all the way up to I to the k minus 1, I to k, and then finally I to k, j are all arcs. Okay. So here's what it means to be connected. Definition. If there exists a path between each of the n choose 2 distinct pairs of nodes, we say that the graph is connected. Where we're thinking we have n nodes. So to be a connected graph between any two nodes that you pick, there has to be a path between them. So if you can find two nodes that there isn't a path between them, then that's not a connected graph. So I want to do some examples. And pictorially, when we think of connected, what we're thinking is that we can go from any one spot in the graph to any other spot in the graph by just following the arcs. Okay? So here's examples. So if I say 1 goes to 2, 1 and 2 are connected, 1 goes to 3, and 3 goes to 4, there's a connection between the two. So this is a connected graph. As another example, so if I say 1 goes to 2, and then 3 goes to 4, okay, then this is not a connected graph. And not connected means disconnected. And the reason is that there's no path between 1 and 3. There's no path between 1 and 4 either. But there exists some pairing of nodes, some distinct pairing of nodes for which there is no path between. All right. Well, what's a random graph? That's what we want to talk about next. That's the definition. A random graph, okay, is a graph with nodes v equal to 7 nodes here. 1, 2, 3, all the way up to n. So we've got n nodes. And arcs, A equaling the pairings I up to, paired off with x sub I. I runs from 1 to n, where you can think of x sub I are independent random variables such that the probability that x sub I equals to j equals to 1 over n, for j equaling 1, 2, 3, up to n. Okay, so a random graph we can think of as kind of an experiment, it's the outcome of an experiment. So we're creating a graph, and what we're thinking of is this. We got these n nodes. So we got these n nodes, and we're going to connect each node somewhere. We're going to have an arc from each node to another, to a node. Might be to itself. But for each node, where it gets connected to, if you will, an arc established between it and some node, is random, and the chance that it gets connected to a particular one is 1 out of n. So every spot that the ith node could get connected to is equally likely to occur. So this means that there's an n to the n number of possible outcomes for a random graph. And each one of those outcomes are equally likely to occur. So that's going to be important. What I just said is important, and an example that I'll have you do, assignment and homework 4. Okay. Now, we will be interested in determining the probability that a random graph is connected so we're going to do work for that and come up with a theorem that will be dependent upon a lemma. And we'll have to do construction to make this theorem and lemma be manageable. And that construction is something called a supernova. So we'll be examining that. And of course, we're going to be doing our work based on conditional probabilities. That's why it's something we're talking about now. So this is an example of conditional probability being useful. But in the example that I'll give you, the homework, not example, in the homework problem I'll give you, so the way that we can compute the way that the probability that a random graph is connected is that if you were to write out all the possible random graphs and then look at the number of them that are connected, the probability that that random graph within nodes is connected is the number of outcome random graphs that are connected over the number of possible outcomes for the random graph, which is n to the n. Okay, so that's the way we can do it, but we're going to come up with a formula for it. Rather than having to draw out all the possible outcomes and look at that's n to the n, and look at the ones up, determine which ones of them are connected. Okay. So in forming a random graph, from each node I, we select, this is what I was saying before, at random, one of the n nodes and that one of those n nodes could be including itself. And join this, and join the ith node okay, with this selected node. With an arc. Okay, so I'll look at some examples and about their connectedness or not. So these are examples of output values for a random graph. So here's my first one. 1, 2, 3, 4. Okay, so I'm going to say 1 goes to 2, and here, this is an arc, but I'm going to put an arrow because this is saying that x of 1 is being sent to 2. And so for each, remember, for each node in the random graph, it has an arc sent from it, if you will. I say sent from it. We think of this as non-directional, but I'm just going to put these arrows so we can tell what x of I is. And then 2 goes to 3, 3 goes to 1, and then 4 goes to 3. Okay. This is a possible outcome of a random graph that is connected. Another example 1, 2, 3, 4 is 1 goes to 2, 3, 1 goes to 2, 3 goes to 2, and 4 has self-loop. Here's what I'm saying. This is not a possible outcome of a random graph. Okay? And here's even if I didn't put the arrows, if I just had this kind of loops, or not loops, but arcs listed here. The reason that this is not a random graph is that if you said, well, this arc is created by 1 going to 2, and this arc is created by 2 going to 3, and this arc is created by 4 being sent to itself, where did 3 get sent? And so, as a fact, here's what we say. Random graphs outcomes have exactly n arcs. Okay, so that's not a random graph. C, we could have 1, 2, 3, and 4 again as our nodes, where 1 is sent to 2, 2 gets sent to 1, 3 gets sent to 2, and 4 gets sent to 3. Now, this is a possible outcome of a random graph that is connected. The reason that I say it's a possible, first of all, we can see that it's connected, but the reason I say it's a possible outcome of a random graph is that I don't know that each one of these creations of arcs are equally likely to occur. So that's the reason I say possible. Let's look at one more example. Part D, example D, 1, 2, 3, 4 are nodes again. And here 1 goes to 2, 2 is sent to 1, 3 is sent to 2, and 4 has a self loop, if you will. And here is a possible outcome of a random graph that is not connected. Okay. We're ready to start working towards calculating what the probability that a random graph is connected. So we're going to look at a construct called supernova. Okay, so in order to determine if a random graph with n nodes is connected, okay, we will look at the following construction. So here's the construction we're going to look at. So starting with some node, say, we call it I sub 0, we note the sequence of nodes, say I sub naught, I sub 0, x of I sub naught, x sub I sub naught squared, all the way up. So x I sub naught cubed, all the way up to forever maybe, the sequence, wherever it ends, where x sub n of I naught is defined by its x applied to wherever x sub n minus 1 of I naught is, that node. Okay, so here we let n be defined to be the first k, so the first number, such that x to the k is not a new node. Okay, we'll look at an example of that next. Okay, so for example, here we'll write down 1, 2, 3, and 4 as our nodes, and we'll have 1 get sent to 2. 2 gets sent to 3, 3 gets sent to 1, and 4 gets sent to 3. And if we consider I sub naught to be equal to node 1, okay, then x of I naught, which is equal to x of 1, that's equal to 2. So 1 is sent to 2. X squared of I naught, I'll stop writing on naught, that's 1. So that's x squared of 1 is really x acting on the random variable x acting on x of 1, which is equal to x of 2. And where does x send to? It sends it to 3. Now, x cubed of 1 is really x acting on 3, and that's sent to 1. Okay. So n, which is what we were looking at before defining on the previous part of the board, is equal to 3 in this case. Because 1 is a node that was already in our list. Okay. A little fuzzy there. All right. So here's what we're going to do. to obtain the probability that a random graph is connected with conditional mean. Okay? So, the probability, and I'm not going to write down random graph. I'm just going to say probability that we know it's a random graph. All right, it's a random graph. So I'll put random in parentheses so they'll stop writing. That a graph is connected. So we're talking about random. Okay. It's going to be equal to a sum as n runs from, or I'll call it k. K runs from 1 to n of the probability of the graph is connected given n equals to k times the probability that n equals to k. So that's the setup for computing the probability that a random graph is connected. Okay, so let us talk about this a little bit. I mentioned that phrase, supernova. So let me give some writing here about that. Now, given n equals to k, the k nodes I sub naught, x sub I sub naught, x squared I sub naught, all the way up to x sub k minus 1 of I sub naught. That's k nodes. Are connected to each other. So I would say that part of the graph, so there's k nodes, that part of the graph, it forms a connected, if you will, subgraph of the random graph. Are connected to each other, and there are no other arcs coming out of these nodes. So they connect to each other, and that's it. To other nodes, I'll say. Okay? Not in I, x acting on I naught, I should say I naught, all the way up to x to k minus 1 acting on I naught. Okay. Now, there might be some arcs. So there's no more arcs going out. They're connected to each other, if you will. They go to that arcs from each one in this group goes to an arc, goes to a node in one of these groups. But there might be some arcs coming in. To these into these k nodes from non I naught, x sub I naught, all the way up to x k minus 1 I naught nodes. Okay? So some node other than this might be having an arc from it sent to this grouping of connected nodes. Okay. So we can consider these K connected nodes as, and here's what I had called before, supernova. Okay. It's a supernova. That's what we call it. And we can consider the graph as a graph having one supernode and n minus k ordinary nodes. Okay. With an arc coming out of each ordinary node. Okay. There isn't an arc coming out of the supernova. Now, note the probability that a particular ordinary node has an arc to the supernode. Okay. So what is this? Okay, so a particular node is not part of the supernode. What's the chance that it gets sent to the supernode? Well, in the random graph, that particular node is sent to some node, possibly including itself, with the chance of that happening being one out of the number of nodes you have, n. And so here, because there were k in the supernode, this is going to be equal to k over n. That's our answer. So in order to progress toward the solution, we examine the following lemma. Which helps us when considering supernovas. Okay, here's the line. Okay. Given consisting of nodes zero, 1, 2, all the way up to R. So there are R plus 1 nodes here. And R arcs given by I, y of I is equal to, and here we'll say I runs from 1 up to R. Now look, that only is R arcs, so I'll say in parentheses, the other arc can be considered as 0, 0, okay, where so here's what I'm thinking. 0 is the supernode. That's what I'm thinking. And we got these R regular nodes. Okay. And so somehow I've got to rewrite, in terms of random graph, what these probabilities of the y sub I equaling to some j is. Here, that's what I'm doing next. So where y sub I equals to j with probability, so that's a particular other regular node, one of the j's, that is one of the j's that is the nodes 1 through R. Okay, so that's 1 over, so how many nodes are there? Really there's R plus K total nodes. So we're thinking in the 0 node that consists of K. That's a supernode, consists of K regular nodes. And then it's equal to 0 with probability. So it's K over R plus K. Okay. This is true for any natural number K. Then, here's the end of the lemma. The probability that the graph is connected that's equal to K over R plus K. And that's what we're going to prove. Now, the proof is going to be done by induction on R. But it's not regular induction. It's something called strong induction. I'll comment on that in just a second. Okay. So the proof is by strong induction on R. Okay. So what do we mean? Well, regular induction is we show that the statement is true for the first natural number, so that'd be here R equal 1, and then assuming that the statement is true for R equal to something, let's say K, we show the statement is true for R equal to N. We show the statement is true for R equal to N plus 1. But in strong induction, what we do is we have to show that the statement is true for R equal to 1, and then assuming the statement is true for every R less than or equal to some generic but fixed natural number N, we have to show that the statement is true for N plus 1. Okay, so it's a little bit stronger in terms of what we get to assume. It's equivalent to regular induction. So here, let R equal to 1. Okay, so what's our scenario? Our scenario here is that we have K nodes in the supernode, and we have only one regular node sitting out there. And so the question is, what's the chance that it's connected? Okay, so then for the random graph, to be connected y sub 1, okay, must be equal to 0, because the only way that the random graph is connected is if that one regular node is sent to the supernode. Supernode 0. Now, the probability that y sub 1 equals to 0, that's equal to k, the number in the supernode, over 1 plus k, because there's only one regular node here, which is the same thing as k over r plus k, and that's what we're going to show. So the statement is true. This lemma is true when r equals to 1. Okay. Now, assume the statement is true for all r less than or equal to some generic but fixed natural number n. We must show the statement is true for r equal to n plus 1. That's what we have. Okay. To compute the probability that the graph is connected in the r equal to n plus 1 case, what we're going to do is we're going to condition. We will condition on the number of nodes, regular nodes, that n plus 1 regular nodes, that are sent to the supernode. I'll write that down now. So we will condition on the number of arcs for which, that's the way we'll put it, for which y sub j equals to 0. So the probability that the graph is connected that equals the sum as I goes from 0 to n plus 1. So here, I said y sub j equals to 0, but maybe call it y sub I. Well, y sub j is fine. That's right. So, all right, so here's what we say. Sum as I runs from 0 to maybe none of the regular nodes get sent to the supernode. Maybe all of them are sent to the supernode. So they're n plus 1, their I is the minimum. So some probability, the graph is connected, given exactly I of the y sub j equals to 0 times the probability, so I can do with space, so it's times probability that I of the y sub j is equal to 0. This is the total law of probability I'm using. It's the sum. And that's the probability the graph is connected. Now I know what the probability that I of the exactly I of the y sub j's are equal to 0. So this is the sum as I runs from 0 to n plus 1. Probability connected given I of the y sub j is equal to 0. Okay, so here we can think of this as like a binomial random variable where we're counting the success if the node is sent to the supernode. And so the chance of that happening, so how many ways could exactly I of these ordinary nodes be sent to this supernode? Well, there's n plus 1, choose I of them. Then it would be the probability of being sent to the supernode for each one of them. That is, so we thought it's k over, so it'd be n plus 1 plus k is the number of total nodes that we have, k in the supernode, n plus 1 ordinary nodes. And then that should be raised to the I, and then times 1 minus that. So this will be n plus 1, if you will, over n plus 1 plus k raised to the, so it would be n plus 1 minus I think. Yes, that's right. All right, so here's what I need to do next is compute this probability, this conditional probability. So, to compute the probability of connecting, and we're going to given I of the y sub j's equal to 0, we're going to relate this to a previous case within the lemma. So we can use this strong induction. We reason that given exactly I of the arcs so you say nodes are going to the 0th node, that supernode, and the remaining n plus 1 minus I, okay, of nodes do not have arcs to the 0 node. Okay. We can view the situation as having n plus 1 minus I regular nodes and a new supernode. zero node, that's the supernode. So this new one, consisting of the old zero node and the I nodes that have arcs. Okay, that have arcs to the old zero node. Okay. Now, the probability that a particular one of the n minus or n plus 1 minus I nodes, say L, okay, has an arc to the new zero node, okay, is, all right, now, before I move there, here's what we know. So L is one of these n plus 1 minus I nodes that isn't directly being sent to the old supernode. So for it to get to the new supernode, it has to be sent to one of the I nodes out of the n plus 1 nodes that was sent to a supernode. Okay. So here it is, probability. The L node has an arc to new zero node is equal to, as I just said, probability that the L node, I'll say, goes to one of the I nodes sent to old supernode, given L is not centered, doesn't have an arc. To old zero node. Okay. That's what we're looking at. All right. That's using the definition of conditional probability. That's probability that the L node goes to one of I node sent to old zero node, and L node doesn't have an arc to old supernode. All over the probability that the L node does not have an arc. So goes to means here, goes to means it does have an arc. Does not have arc. So old supernova. This is equal to the probability that that top just means that the L node goes to one of the I nodes that were sent has an arc to old 0 node over, okay, the probability that L does not go to the I node, I know what that is. That is, so it doesn't go to the old supernova, that's what I should have said. Well, that is n plus 1 over n plus 1 plus k, I think. Yeah, that's what that is. And so this is equal to, so how'd I get that? Well, they're n plus 1 of the ordinary nodes, and they're k in the supernode. So to go to one of the ordinary nodes, it's n plus 1 over n plus 1 plus k, the total number of nodes you have. Now, the probability that the L node goes to one of the I nodes that was connected to the supernova, well, that goes to I over n plus 1 plus k, over this n plus 1 plus k. N plus 1 over n plus 1 plus k. And I'm going to rewrite that, of course, as I over n plus 1, but I'm going to rewrite that one more time as I over n plus 1 minus I plus I. And so I rewrite it this way so that it looks more like the scenario of a lemma. This is my new supernode. I'm sorry, this is the number that's in my new supernode, if you will, sort of. Okay, and this is the number of regular nodes. Yeah. So I'm looking to make this look like that y sub j part of the lemma. Now, the probability that the L node goes, that means has an arc, to a non-new 0 node is the probability L goes to non-new 0 node, which equals to probability L has arc to non-new 0 node, okay, given does not have an arc, to O0. Okay. Same. But we know that in this situation. And what is that? So this is probability that the Lth node has an arc to one of, I'll write it this way, one of the n plus 1 minus I nodes that aren't sent to the supernode given non-new 0 nodes given no arc to O node from L. And that's equal to the probability Lth node has arc to 1 of the n plus 1 minus I nodes not involved in new supernode or new 0 node over, so I'm just using the definition of conditional probability here, over the probability that the Lth node doesn't have an arc to O0 node. And that's equal to, so here, this is going to one of those is, to a particular one, is 1 out of n plus 1 plus k over here, going to the O node. So that would be, if you will, 1 minus k over, so this will be n plus 1 over n plus 1 plus k. And that's equal to 1 over n plus 1, or if you will, 1 over n plus 1 minus I plus I. And so that's the second part of the y sub j in our original lemma. Or maybe that was the first part. That was the first part. First. So, the situation is exactly like the situation of dilemma. Where we have n plus 1 minus I nodes, and k is equal to I, the number in the new supernode, if you will. So as long as I is greater than or equal to 1, by induction, okay, the probability that the new system is connected is I over n plus 1. Okay. And that's equal to the probability connected given I of the y sub j equal to 0. Okay. If I does equal to 0, okay, the probability connected given I of y sub j's equals to 0, okay, is 0, because if none of the non-ordinary nodes goes to the 0 node, it can't be connected, and 0 node's out there by itself. And that's equal to 0 over n plus 1, which in this case is I over n plus 1, which is saying I is equal to 0. Okay, so in all possible cases, the probability of connected, graphene connected, given I of the y sub j is equal to 0 equals to, or is, I over 2 n plus 1. So, when R is equal to n plus 1, then it's more room. Okay, so when R is equal to n plus 1, the probability of connecting, this is for our limit, is equal to the sum as I runs from 1 to n plus 1 is what we have. Probability of connecting given I of the y sub j is equal to 0 times n plus 1 choose I k over the n plus 1 plus k raised to the I and then times, I don't have enough room, I'll put it right here. N plus 1 is what we have over n plus 1 plus k raised to the n plus 1 minus I. Okay, now this is what we just calculated That's equal to the sum as I equals 1 to n plus 1. Here we get I over n plus 1. Times the rest of this. So it's n plus 1. Choose I. K over n plus 1 plus k raised to the I, and then n plus 1 over n plus 1 plus k raised to the n plus 1 minus I. Okay. You can pull out the 1 over n plus 1. This will be the sum as I runs from 1 to n plus 1 of I. And really, it should be 0. That's what it should be. 0. Made a mistake. It should have been 0. Because I could be 0. None of them. That's I n plus 1. Choose, I over k raised to n plus 1 plus k raised to the I, n plus 1 over n plus 1 plus k raised to the n plus 1 minus I. And what we notice here is this sum is nothing more than the sum of I times the PMF of a binomial random variable where there were n plus 1 trials and the chance of success is k over n plus 1 plus k. So the expected value of that, let me write that up. So that's equal to 1 over n plus 1, the expected value of a binomial random variable, with n plus 1 trials and p of probability of success, equaling, so it's that k over n plus 1 plus k. Okay? Which is equal to 1 over n plus 1. All right, what is the expected value of the binomial random variable? It's the number of trials times the chance of success. So this will be n plus 1, that's the number of trials, times the chance of success, is k over n plus 1 plus k, which equals to k over n plus 1 plus k. And that is what we wanted to show in the case where r is equal to n plus 1. So the statement is true, that's the lemma. When r is equal to n plus 1. Okay, so this ends the lemma, ends proof of lemma. Okay. All right. Okay. So, as stated before, trying to prove that the probability in the graph is connected. Okay? Okay. So probability the random graph is connected. So we were conditioning on n equal to k. It's equal to the sum, as k runs from 1 to n, of probability the graph is connected, they're connected, given n equals to k, times the probability n equals to k, where I'll remind you, where n is the first k, where x raised to the k of I sub 0 is one of the previous x, if you will, sub m of I, not here m is between, so it could be sent to itself. M is between 0 and k minus 1. Okay. Now, that's equal to, I don't know, the sum as k runs from 1 to n, k over n, that's the first level, times the probability that n is equal to k, by a dilemma. So all I'm saying is the probability connected given n equal to k is this. Is k over n. By a dilemma, where, let me write this down. Where R in the lemma is n minus k. That's what I got. Now that's equal to 1 over n, sum as k runs from 1 to n, of k times the probability of n is equal to k. Okay, we need to compute this. But before we do, this is 1 over n. One way to rewrite this is k is the output values for n, and probability n is equal to k. That's the PMF for n. So these are the output values for n, and here's the PMF for n. So that's nothing more than the expected value of n. All right, so we got to compute this expected value. Getting very close. Okay, now to compute, we're going to, the expected value of n, we're going to use an indicator function, indicator random variable. So we define I sub I to be equal to 1 if I is less than or equal to n, and 0 if I is greater than n. Now, n will be equal to the sum over all I values, 1 to infinity, of I sub I. So, it just counts for a particular natural number, what I sub I does. But count for this particular little I value, whether n is bigger than or equal to it. Okay? Okay. So, the expected value of n is going to be equal to the expected value of this sum, which equals to the expected value of the sum of the expected values. To infinity of the expected value of the I sub I. Now, this is a discrete random variable, so it will be 0 times the PMF evaluated at 0, so that's just 0, plus 1 times the probability that E sub I is equal to 1. Well, that's just the probability that I is less than or equal to n. This is equal to sum as I run from 1 to infinity of the probability that I, or n is bigger than or equal to I. That's what that is. I'm going to write down one more thing associated with that. So the last thing I'm going to write down, look, in our graph there are n nodes, so the probability that n is bigger than or equal to something bigger than the number of nodes is 0. So our sum doesn't need to run from I equaling 1 to infinity, but just, it can be reduced just to I running from 1 to n. Okay, so now, the probability that n is greater than or equal to I, that's what I meant, can be thought of as the same as the probability that I sub naught, x sub I sub naught, x squared of I sub naught, all the way up to x sub I sub naught raised to the I minus 1 are all distinct nodes. So that's what we do. That's that probability. Those are all have to be distinct. So what does that mean? That means that's equal to the probability that x sub I sub naught equals to some node, we call it j, sub 1, with j sub 1 being different than I sub naught. X squared, or x of j sub 1 then, has to be equal to something called j sub 2 that's different than, I'll say it this way, with j sub 2 being different than j sub 1 and j sub 2 being different than I sub naught. And, okay, we keep going, all the way up to x sub j x sub j sub, I think would be I, so it's same thing as the power. So I minus 1, right? Well, let me write down I sub x sub j I minus 2. So that's what I have. Equals to j sub I minus 1 with j sub I minus 1 being different than j sub I minus 2, j sub I minus 1 being different than j sub I minus 3, all the way up to j sub I minus 1 being different than that's right, being different than I sub naught. Okay, so this is x sub I sub naught has to be j sub 1, where j sub 1 is different than I sub naught. And x of j sub 1 has got to be equal to j sub 2, with j sub 2 not being something a previous node. And, we keep going, and finally, x of j sub I minus 2 is equal to j sub I minus 1, with j sub I minus 1 is different than any of the previous nodes. Okay? That's what we have. These ands, we're having a probability of an intersection, but what we know is that the x's, where an individual node is sent, has an arc going from it to another node, that they're independent of each other. And so the probability of these ands is the multiplication of each one of these probabilities. That's what my right. So that was in the definition, that independence was in the definition of a random graph. So that's equal to the probability that x sub I sub naught is equal to j sub 1, with j sub 1 being different than I sub naught, times the probability that x sub j sub 1 is equal to j sub 2, with j sub 2 being different than j sub 1, and j sub 2 being different than I sub naught, times the probability that x acting on I sub j minus 2 is equal to j sub I minus 1 and, or with j sub I minus 1 being different than j sub I minus 2, all the way down to being different than I sub naught. All right, so what's the chance that I sub naught is sent as an arc going someplace that isn't itself? Okay? Well, what that's equal to is 1. No, I'm sorry. It's n minus 1, I should say. So just being sent to something that's not itself is n minus 1 over n. What's the chance that the next one isn't, that x of j sub 1 isn't sent to itself or the previous one? Well, that's 2 of them, and it can't be out of the nodes. So it's n minus 2 over n times. So keep going. The last one is n. And how many nodes can it be? Here, it would be n minus the quantity I minus 1. Okay, so that's what we have. And so that's equal to, so you rewrite this as n minus 1 times n minus 2, all the way times n plus 1 minus I over n to the n. Oops. And that's equal to, here you could rewrite this as n minus 1 factorial, except I've got too many, so here it will be n, so I want to take away all these. So it'd be n plus 1 minus, I think, minus, so it's n minus I, factorial. Right, that's right. That's right. Yeah, I like to see it from here. And then over n to the n. That's easy to see from here. It's easy to see from here. Okay, regardless, that's what it is. So finally, we're ready to get cancer. We have probability graph is connected. So it's random. Graph is connected. Here's our formula. It's equal to, remember, we're supposed to be 1 over n times the expected value of n, which equals to 1 over n times the sum as I run from 1 to n of the probability that n is bigger than or equal to I. That's what we have. And now we've got something for this. That's equal to 1 over n times the sum as I run from 1 to n. Here we have this n minus 1 factorial over n minus I factorial, and then n to the, it would be, you know, I made a mistake. Oh gosh, it's not n to the n. Oh man. Come on, let's go back here for a second. I wasn't thinking. So here it's not n to the n. How many terms are there? Gosh, there's 1, 2. How many fractions are here? They're I minus 1. So this should be the I minus 1. Make that change. Make a mistake. It's I minus 1. You can count it. There's 1 fraction here. How many n's are there? What's how many fractions there are? There's 1, 2, all the way up to I minus 1. Gosh, that's silly. Sorry. Okay, so this is n to the I minus 1. All right, we can take that n inside, and we will, and take out the n minus 1 factorial. N minus 1 factorial, sum as I runs from 1 to n of 1 over n minus I. And here this will be n. When I pull in the n, it just be to the I. Okay, so let's expand this. So this will be equal to n minus 1 times. Okay, so when I is equal to 1, we have 1 over n minus 1. And this should have had a factorial. Okay. And then it would have been n, and then plus 1 over n minus 2 factorial, n squared, plus 1 over n minus 3 factorial, n cubed, all the way up to, okay, the next to last term, excuse me, is 1 over 1 factorial, so n minus 1 term, I equal to n minus 1, over n to the n minus 1, plus, so the last term is when I is equal to n, 1 over 0 factorial, n to the n. Okay, we're going to rewrite this in a different order, just flip the order. So we get just a nice representation of our answer. That's all. We're essentially done. That's equal to n minus 1 factorial over n to the n. So, okay. So imagine pulling out n to the n off of each one of these guys, and then rewrite it. Okay, so this would be 1 over 0 factorial, switching order. Okay, this would be plus, it would be, will be n over 1 factorial plus n squared over 2 factorial plus all the way up to the n minus 1 over n minus 1 factorial. That's what you get. Okay. So this is equal to n minus 1, we're ready to write that answer, factorial over n to the n. Here this sum is nothing more than the sum as j, if you will, runs from 0 to n minus 1, so we'll have an index that represents this, of n to the j over, this will be j factorial. So that's what this could be rewritten as. And that's the way we can leave our answer. That's the way our book does it. So that's the probability that a random graph is connected. It depends on the number of nodes that it has, and that's what we get. All right, so that's all I wanted to do during this lecture. I thank you very much for your time and patience. This was lecture 25 and 26.